Okay, and I'm trying to get to my pin. There it is. Okay. All right, everybody. So welcome to this next session on harmonic experience, working out of Aladdin Matthews' book. We're gonna be jumping way ahead today. We've gone up to about chapter 9. I told you that'd be a great idea to go back and have some experiences playing through the examples and singing through the examples, because you really have to experience those notes for yourself. But this book is kind of a jump around book in some ways. Actually, the book kind of restarts itself 4 times from different perspectives, one from a keyboard perspective, one from a vocal perspective, etc. And if you go and you look at it and if you read it beginning to end, which I don't recommend that you go read it beginning to end, there's so much there, but it keeps going over the same material over and over again in different ways, and it helps you learn it. So we're going to jump way ahead to chapter 27. If you've got your book, go ahead and take out your book, and we're going to talk about comma phenomena. Comma phenomena. So I think I'm going to erase all of this. Okay, well, here's what we're talking about. I won't erase that quite yet because I'm going to need the lattice up there. We're going to be talking about how in a given key, in our case, the key of C, certain notes, if we're not looking at the equal tempered piano, certain notes are going to have discrepancies in pitch, little small discrepancies in pitch. We're talking a quarter tone maybe, or less. For example, perfect fifths. Perfect fifths are, on the piano, they are off by the overtonal tunings by 2 cents, 2 cents out of 700 cents. They're pretty close, and the 2 cents is perceptible if you really train yourself. I've never heard the difference between a perfect fifth in just intonation and a perfect fifth on well-tuned piano, because they're so close. But there are discrepancies in the numbers, and these start to add up as we go. So we're going to see how there are 4 actual commas, 3 of them that are very usable and very hearable in your music, and 1 that is more theoretical. So we'll start with the one that came first in history, and that was the Pythagorean comma. So look at chapter 27. I'm on page 246 of your book. And I'm just going to read little bits in here where I think it's appropriate. So the word comma comes from the Greek root koma, meaning to cut off or set apart. Let's see. In our written language, it's of course a mark indicating a pause or separation. In the mathematics of musical acoustics, large numbers are often generated by multiplying low prime numbers together, which is what we just did before I started recording this session. We went through all our ratios again, and then some. We stretched out the lattice just a little bit, and we see how those are multiples of 2s and 3s and 5s. Ratios such as 81 to 80 stand for the relationship between the frequencies of 2 tones, and the very small difference between them will be heard as a minute yet specific change in pitch. That is a very small musical interval, something smaller than the intervals that we know on the piano, like whole steps and half steps. Whenever we teach our students that whole steps and half steps are the smallest intervals, we are doing them a disservice, because those are not the smallest intervals. There are smaller intervals. It's just that you can't find them on an equal tempered piano, and you can't find them on a fretted guitar. So that little tiny interval then is called a comma. There's 4 kinds. All right, so let's take a look at the first one. The first one is the Pythagorean comma. And the Pythagorean comma tells me, let's go to this chart, go to page 255. I'm sorry, 253. Here's the 4 commas. Here are the 4 commas compared in this little paragraph in the middle. It says the Pythagorean comma tells us that 2 is not 3. 2 is not 3. What does that mean? All right, let's go back. So page 247. Okay, Pythagorean harmony is all about perfect fifths. As we said, the Pythagorean dimension, like the main spine down the center here, is like a circle of fifths stretched out, right? But here's the thing. Here we go. If we do the math and we figure out all of these, and there's a lot of math in this chapter. It's not terribly difficult to understand if you are a little math shy, like I can be sometimes. But if you go through and you check it out, you can start to figure it out. We're not going to go through all the math here. But what I will tell you is this: if I start on the lowest of C's on the keyboard and I go up each time, I keep doubling, like on Art's keyboard video that he made for us, which is at Montoya's Great Music Theory Practice.weebly.com. You can see that video there. You will see that the same type of thing here. Every time I double, I get the next octave up, right? And if I let's see, is that the chart I want? Oh, okay. Look. Oh, wait a minute. Okay, now I'm talking octaves. I don't want to talk octaves yet. Yes, I do. Look on the right-hand side, example 27.1 on the bottom of page 247. If you look at the notes on the right-hand side, stacked on top of each other, those are all octaves of C. Each time I go up one, I multiply it by 2. So by the time I get to the top C, which is way up here, that's 128, okay? So 1 becomes 2, becomes 4, becomes 8. So I keep octave expanding until I get to that C, and the math comes out to 128. 2 times 2 times 2 times 2 times 2, 7 times. But now look at the long chart on the left-hand side of that. And I start on the lowest C, and then I go up to a G, which is a 3-to-1 ratio. Then I go up to the D, which is another times 3, which is now 9. And then I go up again times 3, which is 27. And I keep going. When I get to the top of the stack, I've reached a note that we're going to call B sharp because it's going by perfect fifths. And what is a perfect fifth? Above E sharp, it's B sharp. And so if you look at these, if you look at the spelling, it's going to have to be called a B sharp. And 3 times 3 times 3 times 3, 12 times for all 12 of those perfect fifths is equal to 129.74634 and a bunch of other numbers past the decimal. 129.75, let's call it, to 128. That's a different ratio. That is a different frequency. That is a different note that is being played. B sharp does not equal C natural. And so we can say that if we're gonna listen over tonally and compound these intervals, a C will not sound exactly like a B sharp. There's going to be a small discrepancy between the two. The math doesn't add up. Does that make sense? Does anyone have a question on that? So when we say that 2 does not equal 3, we're saying that 2's, which are embodied by octaves, do not equal 3, which are embodied by perfect fifths. A stack of perfect fifths does not equal a stack of octaves, and it never will. You can never find something where 2 and 3 are the same thing. That's called the Pythagorean comma. It's almost too difficult for us to invoke in sound because music doesn't usually happen 12 perfect fifths apart. It would have to be music that was only and when do we hear music like that? We don't really hear music called Pythagorean. We have to introduce major thirds to make it sound more like music that we're familiar with to get all of the other intervals, right? So music doesn't travel long. I mean, we might go from C to F, G to C, and that's within 3 perfect fifths on the Pythagorean spine. But we don't just go by perfect fifths all the way up and down to do all those chords. Usually, some experimental music maybe so. So the Pythagorean comma is one that is there, but it's not necessarily as audible. Turn to page 248, you're going to see another example of the Pythagorean comma, maybe an easier way to notice it. So look at this little chart with the diamond notes. C is now in the center instead of starting with C on the low side. How many perfect fifths does it take to get to the last note on the right, which is F sharp? Takes 6 to get there, right? And now look at C in the middle and go to the left. And how many does it take to get to the G flat of the bottom? 6 as well, right? So 6 perfect fifths up is not equal to 6 perfect fifths down. G flat and F sharp are not the same pitch. They're different pitches if you're talking about the true overtonal resonances or tunings. I find this fascinating. So we hear all about the circle of fifths, right? Let's see, let's go down to the last paragraph of chapter 2, page 248. Since modern Western musicians are so used to the circle of fifths as a theoretical concept, as well as a practical learning tool, it may be surprising to some that 12 perfectly tuned fifths stacked from C do not equal a distant octave of C, and that there is hence no circle of perfect fifths. Doesn't exist. But do consider the reason. A perfect fifth is the harmonic embodiment of triple nature, and an octave is the embodiment of duple nature. These worlds are pristinely distinct, as is the prime 2 from the prime 3. Appeal to your intuition. How many times would you have to multiply 3 times itself to achieve an even number that is divisible by 2? The answer is no power of 3 is ever even, that is divisible by 2. And the converse is true also. The truly absorbing issue is the deep quirk of providence by which 12 perfect fifths contrive to come so close to 7 octaves that they nearly, but don't quite touch. Next paragraph at the bottom, musical commas are these narrow but real boundaries that separate. Oh, I like this paragraph, I gotta read it. The salient point is that so close is also so far. Think of instances in real life where entirely different worlds are separated by the smallest boundary. 2 strangers sleeping in adjacent motel rooms separated by a few inches of wall. Oncoming traffic separated by a yellow line. The inside of your body separated from the rest of the world by your skin. Musical commas are these narrow but real boundaries that separate or cut off one harmonic realm from another at a particular point, where melodically, meaning intervallically, they almost touch. The melody is close, but the harmony is far. Okay, there's a neat 2 paragraphs here on equal temperament I'll get back to in a moment. And there's also a nice little video I found on equal temperament, and I'll show you that too. And tuning to A440. Do you know when standard pitch became A440? When? It was in the 1930s, last century. Yeah, we're 20 years into it, Tom. All right, that's the Pythagorean comma. 3 does not equal 2, according to our chart. The back, right? Go back to page 253. 2 is not equal to 3, or octaves are not equal to fifths. If you stack them on top of each other, they won't come out to the same note. The difference between the 2 notes that they arrive at, that's the comma. All right, the next one is called the didymic comma. The didymic comma says that 3 is not 5. Somebody express that for me as it says. What does 3 is not 5 mean? And you'll never get the same note. Very good. So fifths are different than thirds, or fifth partials and third partials too. Okay, so let's go to page 250. 3 is not equal 5. Okay, so there, and again, I told you the book starts over like 4 times, right? So if you go back to the first section, you'll read a little bit about these commas. This is getting deeper into the math and explaining them more. So you can go back and find more about it earlier in the first section of the book. We're now in the second section of the book. So Didymus was an ancient philosopher of the 1st century Greece who allowed pentamerous energy into the Pythagorean system. I don't know how he did that. The dymic comma is the amount by which a stack of 4 perfect fifths exceeds the 5th partial. What's the 5th partial of C? It's E, right? There it is, sitting right above E on the next spine up. It's the 5-4. If it's the 5-4 E, is it the same as stacking perfect fifths to get to that E? Well, let's find out. Okay, so let's look at the diagram. I'm starting on a low C, and I got a 3-to-1, which is a perfect 12th, or like a perfect fifth. So I go to C, then I go up to the G, then I go up to the D, then I go up to the A. So there it was, and then I go up to the E. Sorry, there it is. Okay, that E, which is 1, 2, 3, 4, you see on the left, is an 81-to-1 ratio if we do the math to get from the low C, multiply by 3, by 3, by 3, by 3, we get to 81/1. That's on the left. Now go all the way to, now don't look in the middle here, go all the way to bar 3 of this page. Bar 3 starts going by 5th partials. One octave, oh, wait a minute. I looked at this, it was confusing the first time, and now let me make sure I'm understanding it correctly. Okay, we're just going up. What am I seeing? Okay, it's taking us up to the E, which is the 5th partial in bar 3 before the dotted line. Okay, so here's C, the overtone series to C, to G, to C, to E. There it is, there's the 5-to-1, there's the 5th partial, which we can also express as 5-to-4 if we were gonna octave reduce it, right? Now take that 5-to-1 and then double it, you get 10-to-1. Double it, you get 20-to-1, because every time we double, we get the next octave. Double it again, you get 40-to-1. Double it again, you get 80-to-1. Now we've arrived at the note seemingly that we did in bar 1 using stacked 3-to-1 ratios, right? But what is the ratio of that? It's 80-to-1. And the ratio of the stacked perfect fifths or 12ths is 81-to-1. So that's different. I'm looking at the bottom of this page now. Comparing them, we see that they stand to each other as the number 81 stands to 80, or an 81-to-80 ratio. This ratio represents the amount by which the Pythagorean E exceeds the pure major third. So if you were going to stack Pythagorean notes all the way up to get to E, that's not going to sound the same as if you stacked, if you went for the 5th partial and doubled it. Okay, so 3 does not equal 5. Look down at the bottom chart. Simply stack, here's another way of arriving at the same answer. Simply stack 4 perfect fifths and compare that with the 5th partial. What's the 5th partial? We learned the overtone chord that very first day it came in, if you remember. We went to the piano when we played, okay, this is the overtone, or a chord that we make out of the first 6 partials of the overtone series. That's on the right-hand side. That E, if, now realize I'm just played that in equal temperament, so it's not the overtonal E. First 5 partial E, is different than 4/5 that are stacked from C to G to D to A to E. Those will be two different E's. And then there's a whole bunch of math right here if you want to see different ways to figure that out and see how that works. So 3 does not equal 5. That's the dimic comma. A third up, a major third up, does not equal 1, 2, 3, 4 perfect fifths up. It's two different things. They are two different things, two different pitches. Kind of making sense? All right, there's only 2 more commas. Let's look at the next one. The next is the great diaesis. Great diaesis is the least hidden of all the commas and most sensible. Even in equal temperament, you can sense these things. And here's the thing, you can sense it in equal temperament. It's just not as strong as if you were actually experiencing it in just intonation. And let's go back to our chart at the end. Next page. The great diaesis says that 5 is not 2. 5 is not 2. And I think the easiest way to explain this is to look on the page just before this, 252. Look at the top. On 252, you see a C, then an E, then a G sharp, then a B sharp. Because a B sharp is a major third above B sharp, right? It comes out to B sharp. It has to be called a B sharp, not a C, because that's what it is. And if you do the math, you will find that those stacked fifth partials do not equal a 2-to-1 ratio. C and B sharp, again, are two different things. The upper C, it says at the top of 252, is wider than the B sharp by 128 to 125. The musical interval of this comma, about 41 cents, or almost a quarter tone, is huge compared to the other commas. The difference in just intonation is easily audible, and the effect in equal temperament is enormous, as we shall soon chronicle. So this is one that you can really hear because it's almost a quarter step off. And you can sense that. It's not like 2 cents off in a 700-cent perfect fifth. It's much bigger than that, so you can hear it. In equal temperament, there are circles of thirds, just as there is a circle of fifths. We just mentioned that in order to get pure perfect fifths to be cyclic. Okay, we won't go there. Okay, so the great diaesis 5 or fifth partials do not equal 2, which are octaves. Okay, and there's one last one, and this one is less used. The third functional comma in music is subtle and less common, but can be most artfully employed. It's called the diaschisma. It's the amount by which a stack of 3 octaves exceeds a stack of 4 perfect fifths and 2 major thirds. So what this is telling you is that 2, which is the octave, is not the same as 3 times 5. Fifth partials and third partials together, multiplied together, do not equal octaves. They're different pitches. So go back to look at the diagram here. Look at the diagram we see, and if you see 3 octaves on the right-hand side, if we're going to use G flat, F sharp. If I start on the low G flat, go up a G flat, go up a G flat, go up a G flat. Okay, 4 octaves of G flat. If you have a G flat down here, a G flat up there, but if you follow the lattice harmonic path by multiplying all the ratios together, will it equal G flat? And we find out that no, in fact, it's a different pitch. So on the left, well, in the center, you see C. And if you go up 2 fifths and then up a third, you get F sharp. But if you go down 2 fifths and down a third, a major third, you get G flat. G flat and F sharp are not the same pitch. For the math, let's use this practical computational shortcut, which we've already been talking. Up pa, which is the fifth, means multiply by 3. Up ga means multiply by 5. Down pa means divide by 3, and down ga means divide by 5. Octave reduce or expand is necessary. And I can refer you back to the first steps to harmonic experience, the general terminology page that I put on the website, which talks about sa, re, ga, ma, pa, how this book uses a lot of that Indian notation to explain these things. Okay. Read more of the math if you want to. In fact, I'm going to recommend that you go back and read this whole chapter and check it out again. But let's look at the 4 commas compared one more time. Each comma reminds us in its own way that prime numbers generate mutually exclusive mathematical worlds. The commas are points at which these worlds come into view of one another, but never touching or merging. Pythagorean comma, 2 is not 3. Octaves are not perfect fifths, or stacked. The dimic comma says that 3 is not 5, or perfect fifths are not major thirds. The great diesis says that 5 is not 2, which is major thirds are not octaves. And the diaschisma says that combined thirds and fifths are not octaves. If you are math shy, many musicians are, Dr. Overtone means to assure you that this math is no more difficult than making change, and definitely easier than figuring your taxes. I love how he writes. If you want to skip ahead a little, take a glance at example 34.2. But if your eyes are getting glassy, skip this part and go over to the keyboard where the better stuff is. You may be back through, though, to nail down the numbers. They truly amount to little more than multiplying and dividing by 2, 3, and 5, which is what I asked you guys on the first day. Now, he talks a little bit more about modulation and why that's important when we start talking about commas. So you can go back and read that. I'm going to recommend that you go through and continue to experience the commas or continue to experience the actual tunings of the basic notes like F and E flat and A flat and how that sounds in just intonation by doing the exercises in those first chapters of the book. And then go back and read this whole thing. There's a lot of information here. Next week, we'll sing through the commas and we'll see what that feels like. And that's our lesson today. All right, everybody, we'll see you.